All right, guys, welcome back. Looks like we are just about ready to get started here on installment 3. Hello? Hello? Thank you. Anyway, we'll go ahead and get started. It's like a minute or so after the regular start time, so we'll chit-chat plenty in the break. Appreciate everyone coming back. We're going to go ahead and get rolling on continue the series from last week where we looked at ingredients, and essentially there's 4 ingredients we're considering. Last week was elapsed rates and moisture. Today we will continue along that same path with sources for lift and vertical wind shear. So we'll do the same format we've been doing, kind of a 2-part thing, roughly 45 minutes. We'll take a break. And the crowd size has been good enough. If you have questions while we're going, feel free to interject. That's just fine with me. So we'll go ahead and get rolling here. Again, this is where we are, just in case you're tuning in for the first time or you can't remember what happened last week. This is part 3 of a 9-part series, and this will be the last of the 3 to start this off. We'll have a break coming up next week since I don't really feel like coming in for midnight shifts. So anyone wants to do it for me, that's great. All right. What's the role of lift in severe thunderstorm environments? I mean, we talk about this stuff a lot, but I don't know how much people think about what the real roles of lift are. And we've got different scales that we're talking about. In this case, we'll start with the synoptic scale. We discussed synoptic meteorology, QG theory, that's the kind of thing we're talking about here. It tends to occur over broad areas on the scale of many hours, and what it's primarily doing is conditioning the environment for deep moist convection. However, you don't seem to normally initiate severe storms directly through synoptic scale lift. And I'll show some examples of why that's the case. Mesoscale, however, seems to be our favorite source for storm initiation because now we're getting down on the scale of things like dry lines, fronts, outflow boundaries, and even some of the larger terrain features. And then, of course, we have to consider lift on the storm scale. You know, it does matter because this is what's relevant to the maintenance of squall lines, supercells, that sort of thing. And in our next session, number 4, here in a couple of weeks, we'll talk about this in some detail. All right, comparison of the lift sources. Going back to QG theory, we didn't talk about it in any terms of magnitude, but I'll share that with you tonight. 10 centimeter per second vertical velocity, that's actually relatively strong for synoptic scale lift. Sometimes you'll see people use 5 centimeters per second. We're talking areas hundreds of miles across, acting for hours at a time. So if you have that sort of ascent, you can displace a parcel in the vertical a little over 2 kilometers over 6 hours. So it's not very far. And also you're layer lifting broad areas. You should see clouds forming in broad areas first before you see convective elements. Mesoscale, however, much more concentrated zones of ascent. Now we're looking at updrafts on the order of maybe 1 meter per second. Now they're not acting over as big an area, but you have 1 meter per second updraft for 1 hour, you can displace a parcel almost 3.5 kilometers in the vertical. So that's a lot deeper lift. It's almost twice as far as 6 hours of ascent with a QG type process. And again, if storms are initiating due to mesoscale ascent, you're going to see them form generally in points or in narrow bands, that sort of thing that scales with the size and area of the vertical motion. And of course, we can't leave out the supercell mesocyclone process. 10 meters per second is on the low side for some of the strong storms. 15 minutes at 10 meters per second, you've ascended 9 kilometers. So you're all the way up to near 300 millibars. So it does not take long when you're talking about something on the scale of a thunderstorm updraft to process the parcels. And of course, the core of these updrafts are much stronger, can be an order of magnitude stronger than that. All right, we're going to look at an example with storm initiation. I'm just going to show you the soundings. And just think, when we talked about the soundings, just think about what processes might be acting here. This is a Norman sounding out in the warm sector. So what happens when we have QG type ascent acting on this profile? So I gave you the types of displacement. So I modify the sounding starting from the low levels and we lift the parcels. This is what happens to the sounding with 6 hours of 10 meter per second type ascent. So you see, we don't reach an LFC for parcels. We just primarily moisten and cool the profile from below and erode the convective inhibition from below. But we generally probably have not initiated storms at this point. Okay, what happens when you have mesoscale ascent? Again, we illustrate that. This is 1 hour of 1 meter per second. What do you think's happening at this point in this sounding? Do you think the sounding really would look like this? Or have we already probably initiated storms? So yeah, we have probably initiated storms. 1 hour of ascent, and this would be something equivalent to like the dry line circulation. Now, you want to take it to an obvious extreme. This is 15 minutes of 10 meter per second ascent. This is something like you would see in the core of a supercell mesocyclone, or even more rapid than that. So the parcels ascended through almost the entire depth of the troposphere. We have clearly done a lot of modification. So it doesn't take supercells long to change their local environment with updrafts, forced updrafts in the low levels only on the order of 10 meters per second. All right. Again, a lot of this gets back to, do we reach a level of free convection or not? Again, that's where we've overcome the inhibition. Now buoyancy comes into play. Again, QG ascent usually doesn't initiate storms. It sets the stage. It makes the environment more favorable for storm initiation through cooling and moistening of the profile. But rarely is it the first order process that's initiating the storms, especially surface-based. Mesoscale ascent, again, this is equivalent to like the dry line. I just want to make sure that you guys are familiar with the orders of magnitude of these processes. And then, of course, storm scale, it maybe takes 5 minutes to lift parcels from the boundary layer up to the level of free convection, sometimes even less than that. So that would be akin to a supercell storm reproducing itself through propagation. It's regenerating itself very quickly. All right. Just kind of look at this. I'm going to step through these satellite images. This is a storm case out here in Oklahoma, Kansas, Texas. And I want you to just kind of pick, you can pick any particular area you want, and just watch how the storms form and think about what we just talked about. You know, do you see broad areas of cloud cover forming? Do you see small points or bands? What does it look like from satellite alone would infer or imply the actual source of initiation without having any other observational data? So again, I'll just kind of step through this, and we'll do it a couple of times. And again, just sort of pick whatever place you want to focus on. And we're going to look at western Oklahoma in this example coming up. And think about what might be acting in this particular case. And we'll do it one more time. All right. So this was an interesting severe weather event. It's actually May 24th of 2011, so that was more than a little interesting. It got a little too interesting here locally. Okay, so again, with storm initiation, think back. You know, and again, you don't have to answer this question right now. Did you see large areas of cloud cover forming that were preceding initiation that would suggest there's broad areas of ascent? And we'll look at some more information with this. Okay, now here's the soundings from that day. We'll go to 12Z to 18Z. So again, consider the sources of lift. Think about when we talked about the soundings back to week 1 and some of the examples I showed. Just think, is this a case where it looks like large-scale ascent is acting on that profile? It looks like there's warming and moistening in the boundary layer, typical daytime heating and a little bit of mixing, but we don't see the characteristic moistening and cooling above the moist boundary layer. So in this case, the soundings themselves suggest there's not a lot of large-scale ascent acting on this profile. And this is the closest thing we can get to a warm sector, pre-dry line type sounding. All right, so again, thinking about what we were saying, just focus on western Oklahoma, the initiation area. Again, it doesn't look like big layer cloud areas. We have stratocumulus in the top of the boundary there. Those clouds are already there. But it looks like the storms are initiating in very small points and short bands. That's something that would be a dead giveaway that it's ascent on the mesoscale is acting on this. All right, so the mesoscale, which we're talking about updrafts on the order of 1 meter per second for an hour. You can displace particles or parcels up to 3 to maybe even 4 kilometers in the vertical, which is higher than your typical level of free convection. So that's more than enough ascent to initiate storms. And again, they'll have that characteristic signal in satellite or radar. They'll start at points or in small, narrow bands. Now, let's look at some of the sources for lift. This is going to be a little bit of a review of week 1. Go back over some of the QG stuff. Again, we've mentioned differential cyclonic vorticity advection and warm advection. Those two were term 1 and 2 from the week 1 scaled down QG discussion. Jet streaks, we talked about the straight jet streak where we have the ascent in the left exit and right entrance regions of the straight jet. And then we talked about the modification that occurs when we have a curved jet, where it's not so much the 4-quadrant model and the ascent actually extends over the jet axis and a little bit into the right front quadrant. All right, QG omega examples. Here's one from this past fall, Northeast Gulf Coast. I've sketched in the little red dash line. That's just the convective band based on lightning and radar imagery. And there's a surface warm front that has moved north into southern Georgia. Widespread clouds, you can infer there's a lot of ascent going on in a broad band. And we go to the radar image, and there's a broad band of precipitation with thunderstorms on the leading edge, demarcated by the red dash line. So we had storms in this case. There was severe weather into southwest Georgia and southeast Alabama. Looking at it on a large scale, here's the associated shortwave trough. This is straight off the SPC mesoanalysis page. This is the differential cyclonic vorticity advection in blue in the 700 to 400 millibar layer. So everywhere we have blue, that's CVA increasing with height, contribution of vertical motion. That's a little, it's just, and you notice the convective preset band is just on the leading edge of that, and it's pretty typical to see it this way. We look at the other term. This would be the thermal advection term. We have warm advection is focused more into North Georgia and the Carolina Piedmont area. And this is common, where the differential CVA and the thermal advection don't coincide exactly. So this is a pretty typical example where you might see low-level cold advection beneath the differential cyclonic vorticity advection with a typical trough setup. And just to show, since we talked about the height tendency equation, if we go back where the vorticity advection has been strongest and cold advection maximized below that level, that's where the strongest height falls occur on the order of 150 meters over Mississippi. So this tells you in the short term which way this trough is moving, which is essentially toward the east-northeast. All right. Another QG example. This is one from here locally. We got a little lucky. We at least had a storm. It was back in December, and I think it was the little mini supercells here mid-December. This is a water vapor imagery where we show, this is sensitive to water vapor mainly above 700 millibars. So this is the middle and upper parts of the atmosphere. You don't really see low-level moisture with it. And I've got 500 millibar heights and vorticity on here. And I've sketched in the surface boundaries from a surface map that coincides to this time. So that fuzzy white area near I-35, those are the tops of some relatively shallow thunderstorms that seem to coincide with the dry line. What do they also coincide with? I mean, does it look like there's cyclonic vorticity advection going on? It might be pronounced. You see the dash contours and the height contours cross one another. That implies strong cyclonic vorticity advection. And if we use the typical assumption that this system, that vorticity advection increases with height, then there's some forcing for ascent, coincident with the dry line. So this is a case where we may have mesoscale and large-scale processes acting. And again, just to show visible imagery, you can see the thunderstorms coincide with the dry line here in central Oklahoma. So we also have the circulation with the dry line itself, and we have the large-scale forcing for ascent. Again, the dry line's not terribly convergent. This is the vertical vorticity and convergence fields. So the convergence are the red contours. It shows weak convergence into western central Oklahoma. It's not particularly strong there. But when we go aloft, same image as before, just a different color background. That blue corridor across central Oklahoma is strong differential cyclonic vorticity advection. And again, it coincides with the dry line storm. So this is a case where we probably have multiple scale processes contributing directly to initiation and certainly to priming the environment for storm initiation. And you see, which is typical, there's also more widespread precipitation on the leading edge of this band of a forced descent, Kansas into eastern Oklahoma. All right, As I mentioned before, it's not uncommon to see differing term contributions. Here, this is a 700 millibar thermal advection. It's actually cold advection at 700, which is directly beneath the differential CVA zone. So this is starting right below the bottom of the layer for the differential vorticity advection. In this case, thermal advection does not suggest ascent until you go down maybe a little bit lower, closer to 850 millibars, there is warm advection. So perhaps we have two things going on. We have ascent in the mid-troposphere due to differential CVA, and we have ascent in the lower troposphere, warm advection, and the dry line itself. So again, multi-scale contributions. This would be a case you would expect storm initiation on that dry line if it's the right thermodynamic environment. Show an example of a jet streak. Same kind of thing. This is a relatively straight jet. You know, in the real world, they're not perfectly curved or completely straight. This is relatively straight, so the 4-quadrant model should work. That purple contour in North Texas, that's 120 knots. This is 300 millibars. Again, this is another graphic that's readily available on the SPC mesoanalysis page. And we'll highlight the areas. We'll talk about this again some more, the transverse circulation, the upper branch of it. So we see in blue there's strong divergence over southwest Missouri. There's the ageostrophic component of the flow is away from southwest Missouri, so that's the adjustment process to trying to get the atmosphere in balance. And in this case, what does it look like thermodynamically over the left exit region? In this case, the right entrance region is over the high terrain, high desert area. Not that interesting. Left exit region, however, and this is now we've gone down to 500 millibars, so we're a little bit below the jet core, but same idea. It implies that that's sitting over southwest Missouri, and you see evidence of convection there in that left exit region. And indeed, what happened was through prolonged descent, we moistened and cooled this profile and actually created a little bit of cape, and I think there might have been a wind or a hail report with this. There was one. So it's a case where the environment actually looked pretty marginal for thunderstorms to start with. The modification due to this jet circulation actually created a more favorable environment on the mesoscale in that left exit region. All right, mesoscale sources for lift. We've got a whole myriad of things we can look at. I'll focus on fronts, dry lines, and a little bit on outflow boundaries, but primarily fronts and dry lines. In this case, the front, we talked about frontogenesis as a source for ascent. It's the response of the atmosphere to a tightening temperature gradient. What does the atmosphere do? It warms on the cool side and cools on the warm side in response to the tightening gradient. So it's trying to keep the gradient from getting stronger, and you do that through vertical motion. Now, frontal surfaces slope with height. You know, we think of it as like this one thing, but it's really a three-dimensional surface. So in this case, you have to consider what the structure of the front looks like in the vertical and the horizontal. So where the front is at the ground may not be the same place the front you'd mark it at 850 or 700 millibars. And we'll show one of those to clearly illustrate it. And of course, the dry line, I'll talk about some observational work that suggests how do you tell what the dry line circulation looks like? Because that's not something we're going to have observations to diagnose very effectively because it happens on a pretty small scale. And I'll show another example of that one as well. And of course, outflow boundaries, this ascent is proportional to just the depth and strength of the cold pool. So if you have a weak, shallow cold pool, probably weak, shallow ascent. Deep, strong cold pool, deep, strong ascent. Okay, fronts. Again, you can get into friction and interaction with the ground. The front's usually steep very near the ground, but above that, they can be very shallow sloped. And we see that oftentimes these Arctic air masses that dam east of the Rockies and end up further south than you would expect. It's usually a very shallow cold air mass. In these cases, it depends on the structure of the frontal surface. If the front is very steep and vertically aligned, you can get storms right on the front. If the LFC is low, you can get storms right on the front. However, oftentimes you see storms north of the surface boundary given the shallow slope of that frontal surface. Warm front, same thing, is even more pronounced. The warm front is a shallower frontal surface to begin with, tends to slope up over the cool air. Most convection associated with warm fronts, at least that it initiates with respect to a warm front, tends to be elevated on the cool side of the boundary. All right, here's a frontal case, and this is clearly a winter one. I had to go way down to South Florida. Surface wind shift is moving into the Florida Straits. That's the high temperature dew point air mass. The old tropical air is just southeast of Miami. And nice, nasty, cold, sub-freezing temperatures into the northern parts of Dixie. Not a real good severe storm setup, probably somewhat like it looks this evening. But we see where the front is down there. Now here's frontogenesis, the surface version, calculated version of frontogenesis. It's right down there in the frontal zone. Note, it's across South Florida. Let's go move up to 925 millibars. We haven't gone very high above the surface. Look at where the frontogenetic response and the leading edge of the gradient is. It's quite a bit to the northwest of the surface. Continue up, 850 millibars, it continues even further northwest. Now we're a couple hundred miles northwest of the surface frontal position. 700 millibars, it's all the way into the southeast U.S. We've gone almost the length of the Florida peninsula to track this frontal surface. So the deep baroclinic zone is over the southeastern states, up near the Gulf Coast and southeast Atlantic coast. The shallow part of the front is all the way down in South Florida. Again, just a different way to look at it. This is cold advection at 850 millibars. You see it extends down toward Tampa Bay. 700, it's actually displaced 100 to 200 miles to the northwest. So again, this frontal surface slopes pretty dramatically to the northwest with height. Just to tie it in with the large scale, in this case, remember, the thermal wind arguments. We're going to have a jet core they're going to be geostrophic winds increasing with height above that low-level temperature gradient. Notice where the jet core is. It's up further north. It's above the strongest, deepest portion of the baroclinic zone, not just the response to the shallow front across South Florida. So this is a case where the ascent, it wasn't particularly pronounced in this particular example, but you would tend to look well north of the surface front for any convective initiation, and it almost certainly would be elevated if we have the right thermodynamic structure. All right, the dry line. Now this one behaves a little bit differently. The slope, and it's not really as much of a density discontinuity as you have with the front. And if you're going to get storms on the dry line, you have to look at the depth of the mixing in the dry air west of the dry line. Typically it's north-south. And then you have to look at the depth of the moist layer east of the dry line. So there have been some field studies that suggest that the depth of the entire dry line circulation is about the same as the depth of the mixed layer west of the dry line. Whereas the strongest part of the circulation is near the top of the moist layer east of the dry line. So somewhere you have to look at those heights in the vertical and compare it to the moist side soundings to see if initiation is likely. The other question, how long does the air stay in the zone of ascent? I mean, this is critical. If the parcels are only in for a few minutes, we're talking 1 meter per second, and you can displace it several kilometers over an hour, but what if you only have 10 minutes? You might displace it just a fraction of a kilometer. You may never reach a level of free convection. You won't initiate storms. If the parcels end up detraining, would be the technical term, from the low-level updraft. Well, how do we tell that? You have to look at the orientation of the background flow. Does it keep the parcels parallel to the dry line in the lower troposphere, or do the winds very quickly veer with height? So a bit of a conundrum there. When we talk about vertical shear, most people think, wow, I really want the winds to veer rapidly with height. Stronger vertical shear, right? Well, that's not necessarily good for dry line storm initiation. You've got balance of factors here. In this case, we do want the flow in the low levels to kind of parallel it, and if that means the dry line's typically north-south oriented, you want a relatively deep layer of southerly flow on the moist side of the dry line to keep the air in that zone of ascent so that it immediately doesn't go in, up, and then quickly out over the warm sector before storms initiate. Okay, we'll go back to the May 24th case. This is the surface bound. I've sketched in roughly where the dry line position is here. It's either north-south or north-northeast, south-southwest orientation. Strongly convergent, so that it's a fairly obvious case. Now let's look at the soundings and try to apply this conceptual model of, would we expect initiation? Here's the morning sounding from Amarillo. This is the best we have west of the dry line. And let's say we modify this for what it looks like early afternoon. So you put in the temperature dew point, and we've created a mixed layer. So we talked about this week 1. Now we've got a fairly deep mixed layer. Extends, the arrow shows roughly the depth of that dry adiabatic layer. I didn't purposely draw in a super adiabatic contact layer. I wasn't getting that fancy with it. But the idea is we've got deep mixing. This says something about the potential depth of that dry line circulation. So this goes up somewhere near 600 millibars. So it's a few kilometers off the ground. Now let's go to the east. Best we can do with the sounding on the moist side. This is the Norman sounding from 18Z. if we superimpose the depth of that potential dryline circulation estimated from Amarillo we highlight the top of the moist layer, then we can sort of circle this area. That's the dryline circulation right there where we would expect storms to initiate or not. So we're looking at that depth, roughly somewhere around 875 or 900 millibars to about 600 millibars. That's where all the vertical circulation is going on. Now in this case, does the circulation extend higher or lower than the level of free convection on that sounding? It's higher, right? So initiation is certainly a possibility because the level of free convection is well within the potential dryline circulation in this case. So that's something to keep in mind. And I just overlay the Amarillo sounding, the modified version from the west, so this sort of pieces the whole thing together. And what we're doing here is you're just trying to decide, is initiation more or less probable based on the mesoscale processes? Because again, we don't have observations. These were based on aircrafts flying back and forth, doing transects. You're not going to have that day to day. So you have to come up with an idea, and the reason I approach all this stuff probabilistically is because I can't tell you with great certainty that there will or won't be a storm. I can just say when I know the circulation extends deeper than the level of free convection by a substantial amount, thunderstorm initiation is likely. All right, so again, we look at that case and we do see storms forming. That's the same dry line. Several storms pop up in that zone of ascent, and they appear to originate from little bands of Q. Yeah, Greg?
Yeah, so with respect to the sounding west of the dry line, that would require that you have a good forecast of how deep that next layer is going to be west of the dry line as well, correct?
Yes, the question was, if we're looking at the depth of the mixed layer west of the dry line, we better have a good forecast of the depth of that mixing. I mean, in this case, I purposely used the observed soundings because I vowed to not deal with any model stuff, if at all possible, until way at the end of this, build the conceptual models first. But no, you're right, you have to have a pretty good estimate. Usually, this sort of process works where you could simply put in the expected high temperatures and modify the sounding, or if we go back to what this sounding looked like in the morning, there's a very sharp inversion just off the ground, but it's not going to take much heat energy added to the low levels, and it's nearly dry adiabatic above that. So once you warm up to a temperature that looks like it's in the low 80s based on this sounding, or just over 30 degrees C, mixing will rapidly extend through a much deeper layer. So, and it's one of these, if you look at combine it with this sounding, when we superimpose these, it may not be terribly sensitive because in this case, with the level of free convection lower than 700 millibars, the circulation potentially extends much deeper than that. So we're not on the margins in this particular case, but if you were, that could be important. So this one, it's not particularly sensitive, I don't think, and also with the depth of the moist layer, that is related to the level of free convection, it's related to the buoyancy, it tells you how long parcels will have to stay in the zone of ascent. It sort of fits what you would expect. A deeper moist layer east of the dry line makes it easier to get storms. I mean, some of that's kind of like, wow, genius. I can't believe you figured that out yourself. But in this case, since the vertical motion with the dry line circulation actually scales with the depth of that moist layer, the higher it goes, the closer you're liable to be to a level of free convection to begin with. So the less lift you need, the less residence time you need. All right. Terrain, there's all sorts of other stuff. So we've just talked about two mesoscale type boundaries. In this case, we have heating on sloped terrain. Anybody's lived in the mountains, you see this stuff all the time, or even larger hills. And of course, we have other terrain circulations. We'll talk about this some more with vertical shear. And then we've got essentially differences in land surface. There's land versus sea. There are differences in the rate of heating, and we can create mesoscale boundaries that way. All right. Here's a case of a relatively benign surface pattern. This is a mid-June case from this past year. There's, the point here is that if you look first into southwest Texas, there's weak easterly flow. Now we have terrain back there, the Davis Mountains. You also have a so-called Magic Mountain. You can't see it on this map, but you'll see it on satellite, just northwest of Del Rio, Texas, in northeast Mexico. Scenarios like this, it's relatively frequent to see the initial convection over the highest terrain. So we have heating on the slope terrain, you generate localized updrafts, you initiate storms. and it's easier to reach a level of free convection. So this is pretty common. You notice storms form there before everywhere else, except for the ongoing storms in Louisiana. Now there's all sorts of other mesoscale things on this map, and this is a relatively weak flow case. We have a weak outflow. You can see that moving southwestward. That was from overnight, early morning convection, which is weakening near the upper Texas coast. And we start seeing initiation there near Victoria, Texas, but also there's another feature you see. And this just shows how complex this is. We see the sea breeze, or evidence in the cumulus field on the middle Texas coast of the sea breeze moving inland. So where we get initiation, where the two boundaries merge, we have focused descent, convergence in a smaller area. And then, of course, you can even see in southeast Texas, there's a remnant outflow on the other side, to the northeast side of the old cold pool. We actually get storms formed there north of Beaumont and along the Sabine River Valley. So there's a whole bunch of stuff going on. This is typical of relatively weaker flow regimes, but there's a lot of times, and when you start getting toward the high plains or the Rocky Mountain Front Range, you get interesting terrain circulations that may be relatively subtle compared to these dryline cases we've looked at, and they can initiate supercell thunderstorms on occasion, and I'll actually show you an example of that. Okay, the Denver cyclone. This is another one. Again, it's a terrain-driven feature. Fortunately, the mountains don't move, so we know where it is. And this is just in response to flow coming up and around the Palmer Divide. I don't know if you're familiar with the Palmer Divide. It's just a ridge several hundred feet high that extends east-west through about Lyman. Well, it creates a swirly north of it. In a typical south wind, there's a swirly north of it. That provides a convergence zone. It's also an increase in vertical shear. And I'll show you examples, and we'll talk about this more with tornadogenesis in our next session, but it's a vertical vorticity source, and you can get non-mesocyclonic tornadoes. All right. I've marked in the black line, that's roughly where the Palmer Ridge is. You think of that as being plains, but there's clearly a ridge that extends out east, and it's just north of that is where you get the swirly. That's here, denoted. You see the winds back on the edge of the map in Denver or out of the north or northwest. We've got southeast or south flows across eastern Colorado. You get this gyre, essentially a swirl around the terrain, and that's the familiar Denver cyclone. Okay, so now we'll go to the mesoanalysis, which fortunately I can center this one on Denver. I've circled it. That's the Denver cyclone area. The color fill is vertical vorticity, so we have spin about a vertical axis focused in that zone of cyclonic rotation. And that's also where the low-level convergence is maximized in the red contours. So you would immediately think, gee, this might be an area we'd want to watch for storm initiation. So looking over there, here's a visible image pointing to the area of the Denver cyclone. The sun's out, it's warming up. You have some convection around, but then if you just watch over time, there we go. We get a storm blows up. It's right on the convergence zone. That's also the area where vertical vorticity is enhanced. And it's pretty common, and this is especially true of these June cases, northeast Colorado, you'll get these non-mesocyclonic tornadoes. And that's probably the most tornado-prone place in the world, is just northeast of Denver International Airport. They put it in an interesting spot. It's right on the edge of the convergence zone. So a really great time to fly into DIA is about 3 to 6 o'clock in the evening in June. So if you just do that every day, you'll have some fun experiences at some point. Okay, we have sea and lake breezes that we can also deal with. In this case, ground heats faster than water. Water's got a huge heat capacity, so it's going to be slow to warm. The ground heats faster. We basically generate little mini frontal zones. Once we warm up the land more rapidly than the areas offshore, you create a little shallow cold front, in effect, and it moves inland, and that can be a focus for thunderstorm development. Now, what favors sea breeze stuff? I mean, one thing which is kind of goes against the notion of organized severe storms, is you want relatively weak background winds. If the winds are strong, it tends to wash out the sea breeze circulation. It gets overwhelmed by the gradient flow. You want strong heating over land. You don't want it clear over the water and cloudy over land. That's not a good combination. You'd want the opposite. We better have sufficient cape, not too much inhibition. These boundaries are relatively shallow, so the lift is not going to extend very deep. Usually the storms are subsevere, but the boundaries themselves can enhance vertical shear. Now here's one of this is more fair weather. This is looking at the Great Lakes. This is earlier towards summer. You see the rings around all the lakes. Those are the circulation off the relatively cold Great Lake Erie and Ontario. And also, you get mergers of boundaries in this case. If you look between there, just northwest of Buffalo, you've got a band of enhanced convergent where you have Ontario and Erie both contributing to a circulation. As you get later in the year, these can be severe storm initiation zones, and they can occur with enough vertical shear for supercells. Other things to consider: the shape of the coastline does matter. Concave coastlines. If you look here, it's kind of illustrated like the Florida Big Bend. They're in the kind of north central part. The sea breeze is diverging away from the coast given its shape, so there's not as strong a convergence. But where you have a peninsula or the convex shape, the boundaries are converging in toward the middle of it. So in a general sense, that explains why Florida is such a thunderstorm machine in the summer. I mean, it's convex overall. There are small scale variations, but in general, peninsulas are good locations for thunderstorm development because you have convergence of boundaries from two sides. All right, summarize lift. We get it on many scales. It's weaker when it occurs on a broader scale. It's stronger in smaller areas. And I didn't mention again earlier, but remember with QG omega equation, it's a function of static stability as well. The steeper the lapse rates, the stronger the response in a smaller area. Again, QG ascent, differential CVA, it can be linked to thunderstorm development directly, but largely that and warm advection are priming the environment for deep moist convection. It's usually mesoscale lift. Fronts, dry lines, outflow boundaries, sea breeze zone, any of these kind of boundaries are typically responsible for storm initiation. Sometimes it's even smaller scale, stuff like horizontal convective rolls in the warm sector, if everything works right. And again, you have to pay attention to terrain features. So you can already see this is pretty complicated. There's a lot of things you have to keep track of just on the ascent side of things. Where can I focus storm development? All right, so are there any questions on that part? If not, we can take a few-minute break here, and then we will pick up, and we'll go say 8:15. We will resume with a continuation of this on the topic of vertical wind shear. So if there's no questions, again, we got 7 minutes, I think. All right, we'll go ahead and get rolling here. Gave you guys a bonus 4 or 5 minutes. Okay, we're going to follow up vertical shear. We're going to continue on the tear with severe storm ingredients, and this will be the fourth and final one before we start piecing it together in the next session. Well, we've talked about synoptic contributions to vertical motion and how that changes thermodynamic profiles and sets the stage for severe storms. Well, these same synoptic weather systems are changing vertical shear profiles at the same time. Again, this goes back to week 1. We talk about baroclinic systems. That just means there's temperature gradients. If there's temperature gradients, you tend to have advections. And in this case, a warm advection is a veering wind with height. Technically, it's a veering of the geostrophic wind with height. Cold advection would be backing of the winds with height. So the one we're most interested in for severe storms in the warm sector would be the veering wind profile and warm advection. We also have jet streaks. Well, we have the jet streak itself, and the response is some deviation from geostrophic balance. That changes the wind profile, that response to the imbalance, trying to get everything back. The atmosphere doesn't like the imbalance, so it's trying to restore balance. We have another process, we only hit on it briefly in week 1, which would be lee cyclogenesis. This is essentially air flowing up and over the mountains, subsiding down the east side typically. When it sinks, it warms. It's warming. We can go through the change in thickness of the column. It's creating a warm core low is what we're doing. So if we have maximum warming somewhere just near above the surface, the heights above that will rise. The heights and or pressure below that will fall, so we're creating a warm core low. Well, in creating this low, we induce southerly flow near the ground, which that's coming from a different source region at a lower elevation, and the mid-level flow over the mountains is bringing lapse rates from somewhere else. So we've already set the stage for differential advection with lee trough formation. All right, baroclinic waves, large-scale warm advection. As long as you don't have a warm sector that is completely modified with zero temperature gradient, you should see some veering of the winds with height, even in the open warm sector. Baroclinic waves, the stronger the thermal gradient, the potentially stronger the cyclogenesis, the stronger the temperature advection, the stronger the ascent, the stronger the vertical shear. It's all linked together. Cyclogenesis itself, pressure falls lead to mass influx. I mean, if you remove mass, you're going to replace it from below and somewhere horizontally. So it's going to draw air into a deepening low. Pre-existing fronts give you the potential for stronger temperature advection, stronger ascent, which is also related to a stronger veering wind profile with height, which is stronger vertical shear. Deepening cyclone. Again, we draw air in, we strengthen the gradients, especially in the lower to mid-troposphere. Strengthen the advections. Again, you should get the point here is this stuff is all tied together. Positive feedbacks are common in dealing with these large-scale systems. And when you put this all together, you can actually have these QG processes create favorable large-scale environments for severe storms. Okay, I'm going to show an example of a deep synoptic cyclone, and we'll also focus on the quadrant of the jet. I don't have the reports for this event, but there was a severe weather outbreak with it. Focus on the jet streak moving into the northwestern United States. This is 300 millibars, so we'll start up high and then we'll work through a several-day period, and then I'll go down over different pressure surfaces. So in this case, these are 12 hours apart, so every 12 hours, and this is 0Z on October 26th of 2010. So this is a mid-fall type event. We've got what looks like a curved jet streak. It's moving over the plains. In yellow, if you can see that, I don't know how clear that, I guess you can see it up there. That's strong. That's actually calculated divergence from our mesoanalysis fields. There's an upper air charts. So we've got strong divergence diagnosed centered over Nebraska, but it also extends a little further south. So we've got a strong jet streak. There is some curvature at play, and then we continue. If you look at the area of divergence, inferred it stays over the central northern plains, upper Mississippi Valley for several days. Now, another thing to keep in mind is look at where the Ohio Valley is with respect to this jet streak. And this is up pretty high in the atmosphere, 300 millibars. Right front quadrant, right? Oh, well, you know, the right front's terrible. I know I've said it several times already. It's terrible, it's subsident, nothing ever happens there. Hundreds of severe weather reports in this event, widespread damaging winds and quite a few tornadoes with a squall line that moved across Indiana and Ohio were the centroid of the outbreak. They are clearly not left exit region of this jet streak, and this is common to see this with synoptic waves. So clearly it wasn't strongly subsident, even in this right front quadrant. All right, so we look down a little lower. We'll jump down to 500 millibars and see how the system evolved. So we had a strong jet streak aloft. We can apply some of the curved jet arguments in that case, and it seems to work. Okay, here we go to 0Z on the 26th, the same time I stopped before. Strong shortwave trough, very strong thermal gradients. You can imply strong warm or cold advection into the base of this trough, and I'll show that there was even stronger cold advection beneath this level. So you would expect this is an amplifying wave in all likelihood. So this system is unlikely to get weaker with time. And indeed it doesn't. And at this point, notice the gradient over Missouri now and Illinois. You know, you go backwards. Just in 12 hours, we had 65, 70 knot type flow. Now you see 100 plus knot flow. So the gradient's tightened, the entire jet streak has intensified. And what does that say about the downstream advections? We've created more vorticity. I mean, look at the horizontal difference between, you know, say, pick where Des Moines is in central Iowa. You go from relatively weak flow to 100 knot flow. There's tremendous shear on the cyclonic side of this jet. We're generating a lot of vorticity. We can imply a ton of vorticity advection downstream from that. So again, these are QG forcing for ascent and height fall type processes acting. So it moves up, hole low closes, and occludes. We drop down to 850 millibars. Here's our initial lee trough over the high plains. That's a warm core. Notice the temperatures are warmest along the axis of the trough. Now this is that next evening. This is the time where the system really began to rapidly deepen. We've got the baroclinic zone now out in Kansas and Nebraska. So we've got the sharp thermal gradient is sitting right beneath the mid-level trough, so there's strong cold advection. Beneath that, again, think back to the height change argument. It's differential thermal advection in the height tendency equation. If we're shrinking the column down below, the heights above that are going to fall. So this is a mechanism to get the deepening of the system aloft beneath or above a level of maximum cold advection below. And again, very deep low forms. You look at this point, the front itself is a lot sharper into Illinois. Thermal gradient stronger, advections are stronger. And look at what's happened in response to cyclogenesis, the winds. There's a lot more 50 knot plus winds in the warm sector. And what this also feeds back to the thermodynamic profile. Now we've got stronger flow, stronger advection. We draw more moisture further north. We set the stage for severe storm development. And then we can, just a quickie version of the surface map. The red would be warm front, brown's a dry line. My simple version, initially lee cyclogenesis, downstream from the high terrain, northern Rockies. System, cold front surges south, overtakes the dry line, but we've got the main surface cyclones in the Dakotas there, and then you see that this rapidly deepens. It ends up being a deep cyclone, but then we have strong flow and strong moisture advection all the way into the Ohio Valley up toward the lower Great Lakes, or they're at least Lake Michigan area. Again, this was a case that destabilized rapidly, and we had a lot of severe weather during this occlusion phase, right through here. Ton of severe thunderstorm wind reports and tornadoes with this system. So again, cyclogenesis is good because you increase the transport of moisture, lapse rates, and you also change the vertical shear profiles, usually for the better. All right. We have other processes that in action, and typically out here, if you skew a little more toward the plains, we have the lee cyclogenesis, and you can combine factors where you have large-scale ascent in combination with the lee cyclogenesis mechanism. Here's a case where we have pretty rapidly deepening low. That's just 12 hours it's in the vicinity of Goodland, Kansas. This is actually that case I showed you last week where the sounding just fell apart in Norman. So just because there's strong cyclogenesis, that by itself doesn't necessarily mean anything. You have to make sure that everything is in alignment. Again, 850 millibars. Notice tremendous increase in all the gradients. The wind responds, the flow is stronger, advections are stronger. Unfortunately, in that case, or fortunately, depending on how you look at it, we brought drier area in from the south in Texas. So a south wind doesn't automatically equal a more moist profile. And this is the shortwave trough. So if you remember from last week, this is the one where I had you make the call and it didn't actually work out too well toward the I-35 corridor. However, that was not the only single place that was in existence that day. Let's look out by Dodge City where something did happen. So this is Dodge City in the morning. Notice the low-level flow is weak, so we're going to have to strengthen those gradients out there somehow. We've got strong flow aloft, but we need to strengthen the gradient. The moist layer is very shallow. We do have steep mid-level lapse rates already over the high plains. Okay, so we need to increase the moisture, we need to increase the vertical shear if you want organized severe storms. Well, that's what happened as the shortwave trough and the exit region of the jet streak approached. The low-level flow increased dramatically. That brought in what moisture there was up to a relatively high elevation, fairly unstable, and this was a combination significant wind, tornado, squall line type case out in the high plains. All right, jet streaks. Again, it should be kind of self-evident that some of the wind's going to increase somewhere in the atmosphere if a jet streak, which is a max in the winds, moves toward you. You should see an increase. However, it's the responses to the imbalance that really get interesting in terms of what they do to the low-level flow especially. And we'll talk about the flow crossing over in the so-called transverse circulation. We hit on it a little bit week one. We'll do some more here in a little bit more detail. Okay, the straight jet model. Remember, air moves through the jet streak. The air parcels are moving faster than the jet itself is moving. So it moves through, and what we have is in the so-called thermally direct circulation, that's the fancy name for it, that's the entrance region. Thermally direct just means we have rising in the warm air, sinking in the cold air. So as the parcels move in, we're trying to weaken the gradient. They're encountering a stronger gradient associated with the jet streak. The atmospheric response is to weaken that. So what it wants to do is it wants to cool the warm side and warm the cool side. That's where you cool the warm side by ascent on the warm side. That results in the cooling. So that's part of the reason why our right entrance region is often characterized by ascent. The air leaving the jet streak, it's the exact opposite. We want to strengthen the gradient because it's exiting the strong gradient region. You cool the cold side, which through ascent, which is in the left exit region. All right. Again, the air moves through the jet streak. I just put all that into words. The interesting part here is that there's that transverse circulation. We actually create more of a three-dimensional circulation response to the imbalance. And I'll show you what that does to the wind profile and why it might be important. But the important thing here is that if we take a westerly jet streak, which is the cases we've been using, the low-level response in the exit region of the jet is to enhance the low-level southerly flow. So just think about that for a minute. And if you do that, we're automatically creating a more interesting shear profile in the exit region, and if there's buoyancy associated with that, you can have a severe storm risk. Okay, so we're looking down from above, simple jet streak. This is the part of the transverse circulation aloft, so these yellow arrows are the direction of the pronounced ageostrophic flow aloft. It's from the away from the left exit region and away from the right entrance region. So that infers divergence over those two areas, and then meanwhile the right entrance, or the left entrance and right exit are convergent aloft. Mass continuity, first thing you would think is, wait a minute, that might be a contribution to rising motion where we expect it and sinking motion in the other quadrants. Low-level response is the opposite. So in this case, we have enhanced southerly flow with the westerly jet streak in the exit region. Now, what's typically to the south? Is it more warm and moist on average to the south? Yeah, it is. So you're going to increase moisture transport in that exit region northward. You're going to potentially bring a more unstable thermodynamic profile further north than you would otherwise. All right, so again, this is just the same four-quadrant model we've talked about before. Now, if you just sort of illustrate it, this is what you're doing. This is like the high-level jet flow and then the low-level response. Notice they're opposed to one another, so this is 90 degrees veering of the winds with height just based on that response. And then we'll just go through it like one more time. So again, I'm just focusing on the exit region here because that's we could look at the entrance region, but again, the low-level shear is not enhanced to the same degree. All right, now, flip your perspective around. We are looking back to the west. Air is coming at you out of the screen. We're looking at the jet core. and it's strongest somewhere in the middle and upper troposphere. So if you look at what the circulation in 3 dimensions looks like, the exit region is the purple and red side. So those magenta vectors, that is the ascending branch of that circulation in the left exit region of the jet. And then you have the subsiding portion of that transverse circulation in the right exit region. So again, it's 3-dimensional. The response of the atmosphere is in 3 dimensions. It's not just simply on one horizontal surface. This is a full 3-dimensional response that's going on. All right, differences with a curved jet. Again, the divergence aloft and the ascent are stronger near the jet core, and it actually spills over a little bit into the right front quadrant, or what you might call that. And you have the low-level response, but again, it's skewed a little more toward the worm side of the jet. Where is it usually more unstable? That direction. So a curved jet pushes the response exactly in the direction where we typically have the buoyancy. So you don't have to work as hard to get some alignment spatially of the buoyant air mass with the stronger vertical shear. And again, that right front quadrant, which some people are so afraid of, is actually many, many severe weather outbreaks occur there. All right, Lee cyclogenesis. Go back over that. You have subsidence and warming air. It goes up the west side of the mountains, comes down the east side. It warms, it dries. We create a warm core low or a trough east of the Rocky Mountains. That results in pressure falls, draws air in from the south. We've already established that we have westerly flow, so now we've got differential advection going on. This can happen ahead of the primary quasi-geostrophic forcing for ascent. So it kind of gives us a head start on developing this whole loaded gun profile. So we don't necessarily have to have anything particularly intense going on the large scale. And this is one of the reasons the Great Plains of the U.S. are so favorable for severe storms. All you need is westerly flow over the mountains, and in a sense you've got, by and large, created a vertical shear profile and through differential advection, a thermodynamic profile that favors severe storms, just through geography alone. All right, where do we tend to see the lee troughs? The most obvious one, this is a terrain map with the dark oranges or reds there. That's the highest area. You notice it's in Colorado. The most common area for lee cyclogenesis is eastern Colorado. That's because that's the highest terrain in the Rockies, is right there, and it's the most continuous high terrain. But you see lee trough responses all the way down into West Texas and up into Montana. Another common area is in the lee of the Appalachians. Now, of course, the Appalachians are shorter. The mountains are much shorter than the Rockies, and they're oriented different. So the lee trough response isn't as strong, but you do see it, especially into the late spring and summer. You will know. If you do surface maps, you see it all the time, but when it's co-located with a moist air mass, it tends to be in the summer. And of course, there's all sorts of other little mountain ranges and terrain features that you get these responses to. It's just they're on a smaller scale. All right, here's a case with lee cyclogenesis, and we'll show the deepening of a surface low before you actually get the arrival of the synoptic wave. This one, you notice the shortwave trough, this is 500 millibars, is back over the Great Basin. So it's still mostly over Nevada, Utah, and northern Arizona. And this is as of 0Z. But we have flow across the high terrain in New Mexico and Colorado. So you would expect the lee cyclogenesis, even though the stronger jet core and the stronger synoptic scale forcing for ascent, you can imply that it's back to the west. Low levels, again, these are every 4 millibars, so it's a pretty crude surface pressure analysis, but we get a low that deepens over towards southeast Colorado, and this is ahead of the primary synoptic wave. Now that's related to something here. Some of you may be familiar with the low-level jet, and especially these evening ramp-ups. You'll see it the low-level shear rapidly increase in the evening. Well, it's related to lee cyclogenesis, and it's related to the slope terrain. So it can be very relevant to occasional tornado events. So again, we've got 2 factors. Now I'm not going to go into the details here because we can go off in the weeds really quick, and I don't want to do that. So it's a diurnal variation and vertical mixing. Essentially, once you shut down the mixing process and you start to cool and decouple the surface layer from the layer aloft, you get this so-called inertial oscillation. You want to know the gory details, dig around in dynamics, and if you don't, just trust me, it happens. There's also a diurnal variation in the rate of heating and cooling with sloped terrain. This is sort of a thermal wind argument. Point is, nobody's actually sure which one of these is the dominant contribution. So there's a lot of work being done on this. And I think there are people right now in this building working to consolidate these ideas. But the point is, you can get a rapid increase in low-level shear in that like 0 to 3Z time frame. And it happens pretty consistently over the high plains. Again, when this coincides with a sufficiently moist, buoyant profile, you can actually see a ramp up in the tornado risk, even though you're after the diurnal cycle. It can be getting dark and the tornado risk actually goes up. And did anyone happen to recognize what the 500 millibar chart was from in the previous case? It was Greensburg, Kansas, so maybe it was relevant that evening? I don't know. I mean, that's why I'm talking about it. Okay, so what we have here is a sample, and this is some work that I was involved with, where we, on the left, highlighted in the red box, these are significant tornado cases near and after dark over the plains. And on the right would be the blue highlights the non-tornadic cases. So what we're doing is we're looking at the top box, that's the 0Z analysis of the low-level jet, 3Z. So we're just going like a 3-hour change in the low-level jet. You notice they're pretty similar patterns for the tornadic and the non-tornadic. They both increase pretty dramatically from just in that 3-hour period. And the magnitudes are slightly stronger in the tornadic cases. That's 20 meters per second, which is about 40 knots. And remember, this is kind of a smeared out mean for dozens of cases. But the point is, this is a pretty constant process. You see this all the time in the evening out over the high plains. Low-level jet, the surface decouples, low-level jet ramps up, especially in the cases where there's a deepening lee cyclone. You may be well ahead of the synoptic wave. Well, that low-level jet ramp up is pretty consistent, but what's not consistent from case to case is the distribution of moisture and convective inhibition and that sort of thing. So again, you can actually have the tornado risk increase after dark, and it's related to the low-level jet is the transport mechanism to get the higher moisture content somewhere where it may not have been earlier. Okay, so this is an overlay of sounding. This is actually the Greensburg case itself. This is like our best guess from the Ruck model analyses. Highlight the hodograph changes first. So you remember our hodograph is just the connection of all the vector winds, and it represents the vertical shear. The dark red is the earlier hodograph, and then the lighter red, that's what you notice the increase in the curvature and the increased expansion in the size. The low-level vertical shear more than doubled just in the 3 hours. So something like storm relative helicity increased dramatically. If you look down low, we did cool. So the boundary layer did cool, and in a sense it became more stable. But what happened to the moisture profile? The moisture increased simultaneous with the cooling surface temperatures. Well, that's going to lower LCL heights and reduce evaporation potential. But in this case, the moisture increase is more important than the temperature decrease. Because if you look at like mixing ratio and you play around with the sounding, you get more increase in CAPE with increases in mixing ratio than you do for some sort of corresponding increase in temperature. So it's more sensitive to moisture than it is potential temperature. So in this case, we maintain large CAPE. We had a little bit of inhibition, huge increase in shear, and if you have a storm that moves into this environment, then you have to consider something bad might happen. Okay, so this is what happens locally, where the storms were observed. And this is interesting just by itself. So the arrows point in time. So the left side is 0Z, the right side of each of these box and whisker plots is 3Z. So notice the tornadic ones. This is in the location where the tornadoes occurred. From 0 to 3Z, locally, the buoyancy actually increases. Well, there has to be horizontal advection going on to see something like this. Usually, the dry line mixes through close to where the storms occur, and then the moisture surges back in the evening, and you get a big increase in CAPE. So it's actually getting dark, and it's getting more unstable locally. It may not be more unstable than it was out in the open worm sector, but locally it's destabilizing. Well, you see the same signal in the non-tornadic cases, it's just the magnitudes are reduced. It's not a strong increase, but that's counter to the diurnal cycle. You wouldn't normally expect CAPE to increase locally as you get dark. If we look at the convective inhibition, pretty big difference between the tornadic and the non-tornadic cases. The tornadic one's much weaker convective inhibition. It increases, but just not as dramatically as you see with the non-tornadic one. So what we're doing is we're creating a kind of an unusual profile where we maintain buoyancy, we keep the cap fairly weak, and we drastically increase the vertical shear, all just past the peak heating cycle. So if you're not paying attention to this, you might be surprised, or, and of course I know in the past chasers would go home, and the big tornadoes actually occur behind them, right where they were sitting 2 hours before. Okay, so now let's look at another topic here just real briefly, the outflow boundaries. I have a whole lot more stuff on this when we talk about the tornado patterns. We'll look at some cases. They're baroclinic zones. They change the vertical shear, especially on the cool side of the boundary. It's usually, typically, they can be oriented any way you want. If with an east-west outflow boundary, typically it's a more easterly flow or a backed wind on the cool side. New cold outflow is typically characterized by backing winds with height and cold advection. Again, it's a smaller scale cold front. The more interesting case for tornadic storms would be the modified outflow, where you've got weak low-level warm advection and veering winds with height on the cool side of the boundary. So we're modifying the profile. It's essentially starting to behave more like a warm front as opposed to earlier behavior like a cold front. They don't just occur in the plains. I know a lot of the examples, it's easy to find them out here. You can get these outflow boundary cases almost anywhere. This is a pseudo dryline case, western Arizona, with the intersection with an outflow boundary. And that storm that's right where the two boundaries intersect, that's a supercell that's ongoing in southwest Arizona. Again, geography only matters. It only matters to the extent that you set up the environments. In this case, you had dew points in the 60s at the surface. You had some buoyancy, you have a synoptic wave. The storms don't particularly care that it's Arizona versus Florida or Oklahoma or whatever. All right, what do these outflows typically look like? I've marked the site of the Lamont sounding there roughly in northern Oklahoma. Here's a large MCS moving by just before the balloon is launched. This is what it did down in the low levels. So the outflow is just this shallow layer in the low levels. You notice the wind is more out of the east, it's cooler, it's more stable, but it's not very deep. So it's a relatively shallow, and that's pretty typical of a lot of convective outflows. And here's what a case looks like in the afternoon, where the outflow boundary is retreating to the north. This was from this past early fall. And you still have a memory of the baroclinic zone there. The winds are back to more southeasterly toward the Kansas-Oklahoma border, where it's more southerly flow in the open warm sector. That gives you a source of convergence. You can see it in the cloud field. There's a convergent boundary, and eventually supercells formed in the vicinity of this outflow. All right, sea breeze boundaries. In this case, I'm specifically talking about Florida. It's the most common area to see this. You see it all along the Gulf Coast and sometimes the Atlantic coast as well. Typically there, if you're considering the East Coast sea breeze, it's going to move inland further when you have weak background easterly flow. And the converse is true for the West Coast sea breeze. And again, these are frequently augmented by storm outflows. But you can also increase the vertical shear locally due to the changes in the wind direction and speeds with these outflows. Okay, here's a sounding from Miami. This is June of 2012. Thermodynamically, the lapse rates are not particularly steep by plane standards, but they are conditionally unstable. They fall somewhere between moist and dry adiabatic. We do have buoyancy. Vertical shear leaves a lot to be desired. The flow's weak down low. Really, there's no more than 20, 25 knot winds all the way up through 300 millibars. So this kind of scenario, you wouldn't just jump out at you as a huge severe storm or supercell type risk, just glancing at this 12Z sounding. Okay, let's look at by afternoon. We jumped ahead to 21Z and see what's going on. This is the SPC mesoanalysis. I've highlighted, point the arrow toward the warmest temperatures. That's where it's warmed up into the upper 80s. There's been some mixing inland, but it's warm. We've mixed, it's a warm season case. So we continue there. Surface-based Cape, there is buoyancy. It's a little stronger toward North Florida, but there is buoyancy inland over South Florida. Deep layer vertical shear, this is the effective bulk wind difference, 25 knots maybe. We're kind of way on the lower margins for organized storms. Effective storm relative helicity, 25 or even less. So the low level shear is really piddly in this case. And the supercell composite, just a reflection of that. There's really no substantial signal over South Florida. Well, what's actually happening around this time? Notice the storm there on the Florida East Coast that's north of Fort Lauderdale. That's a supercell. It's on the cool side of the sea breeze boundary. You have stronger easterly winds than you have in the rest of the analysis. So the vertical shear is a little bit stronger there compared to the background, just weak southerly flow. Boundary moves inland. Look up at Hendry County, kind of in the northwest part. You see that little echo? We trace the fine line. That's the outflow augmented sea breeze boundary. This thing moves southeast. It's staying on the immediate cool side of the boundary. The shear's a little stronger, high reflectivity. Obvious mesocyclone with this storm. Okay, now keep in mind that sounding that I showed you. This was the day with the largest hail observed in South Florida history. It was like bigger than baseballs with this. If you're not looking at the data, I promise you, you have no chance of catching something like this unless you're actually looking at it in some detail. You just say, it's June, whatever, flow's weak, I give up. And then you have to explain this to somebody. So I don't like to do that personally. I'd rather have a forecast that reflects some kind of threat, and it takes a lot of work, and it takes a lot of attention to detail. All right, we have some other things as we're just about ready to wrap up, so I'm going a little faster than I thought. We have the influence of terrain where you can channel the flow with valleys. The wind doesn't easily move mountains, in my experience, so tends to bank up against the high terrain and it gets redirected. And then, of course, you have stuff like the Denver cyclone, and there's a whole myriad of other little circulations. And we'll show an example in California. The Central Valley is known for this, with high terrain, the Sierra Nevada range, and it's not flooded in the Central Valley, it's just very close to sea level there. So we've got a north-northwest, south-southeast oriented valley. What happens when in a case where the background gradient would suggest the flow should be southwesterly, what happens? It runs into the Sierra Nevada foothills. The air's piled up. As long as the pressure's lower to the north, which in this case it is, the low-level winds are redirected up the valley. So now you've changed the wind profile. Instead of having southwest surface winds, you've now got south-southeast surface winds. If you have a little bit of buoyancy, sometimes you get little supercells in these kind of cases. Again, there's all sorts of places where you see this. If anyone's from back east, the Hudson Valley in New York, it's not as pronounced as the Central Valley, but same kind of response. You'll get enhanced low-level southerly flow in the cases of mid-level westerlies, and occasionally that's the difference between tornado and no, when storms reach the Hudson Valley coming in from the west. So again, we'll summarize the vertical shear, baroclinic waves. They provide background vertical shear, generally through warm advection, responses to the ageostrophic flow with the jet streak. And again, especially in the exit region, which is where that wind profile will be most favorable for supercells. You also get bands of enhanced shear on cool sides of outflow boundaries and sea breeze fronts, that sort of thing. And again, it depends in those cases what the buoyancy profiles look like. And then you get all sorts of terrain influences ranging from the Denver cyclone to the channeled flow to the impact on the plains nocturnal low-level jet. And those can be associated with some very intense tornadoes. So it's not something you would easily discount and get away with it. All this stuff is relevant. So hopefully it's all, you're getting a chance to piece it all together from the first 3 weeks that everything we've gone over, it's all related. Because if you get a handle on that part, everything else is going to make a lot more sense from here forward when you try to improve your forecasting yourself. So just a little hint of what's next. I figure some of you are probably like, fine, he's going to shut up about soundings and all this, and let's talk about tornadoes. So I promise we're going to actually do that. And this is just an example of what's coming up. We'll talk about the flow in supercells. We'll talk about tornadogenesis and what forms and maintains the supercell process in the first place. So it should be entertaining stuff, and I guess if the schedule's right, that'll be 2 weeks from tonight. So that's all I have for this evening's session. If there's any questions, I'll be happy to take them. Otherwise, you guys are free to go.